folks are joining. So let's start maybe in just a couple of minutes.
There's a very nice paper by Reinhard Werner explaining the duality between superdense coding and teleportation. So for whomever is interested in this, should check this out. I answered it in the Q&A to the question by Michael Cedar. Are these talks recorded?
Yes, actually. Is that okay with you? And we're also broadcasting live on YouTube. Okay. Yeah.
Sure.
Okay, so perhaps let's get started. So today's our pleasure to have Felix Leditzky, who will soon be joining the math department just this January as an assistant professor. And he will be talking about the optimality of the pretty good measurement for port-based teleportation. And as a quick add-on, so next week we plan to have our last quiz seminar of the semester, which is planned to be by Lillian Childress. And with that, Felix, please go ahead.
Thanks a lot, Edgar. Thanks for having me. It's a pleasure to talk about my research here. I'm very excited to join in January. So this is also a very good opportunity for me to introduce you to some topics in my research. And so this is actually one of my favorite topics, which has to do with port-based teleportation. And in particular, it's in a greater scheme of things, it's the idea that you use symmetries in order to understand information-theoretic protocols a bit better. So we all know this is a recurring theme in mathematical physics. Whenever you have symmetries in the problem, then they usually simplify the problem a lot by reducing the number of degrees of freedom that you have to account for. And often, only with using symmetries, problems become tractable. A very nice showcase example of this in quantum information theory is spectrum estimation. So in spectrum estimation, you're given an unknown quantum state. You're given n copies of an unknown quantum state rho, and your task is to measure the spectrum of the state. And so just very schematically, you have these independent and identical copies of rho. You're allowed to make some joint measurement on all of these copies of the state, and then the measurement outcome should let you guess the spectrum of the density operator. So by spectrum, I mean just the eigenvalues of the operator. And it helps a great deal to realize the symmetries that you have in this problem. For example, if you're given an unknown state rho, and you're only asked to kind of like make a guess for the spectrum or the eigenvalues of the density operator, every unitary applied to that operator will not change the spectrum. So you might as well take kind of symmetrize the problem and take a state that is invariant under these unitaries, because it will have the same spectrum as the one that you started with. So mathematically, what we say is we have a unitary symmetry and we have a special unitary symmetry, which is acting with the same unitary on each of these states. And the other symmetry that helps you in simplifying the problem is that when you're given n identical and independent copies of the state, then you can obviously permute the states and you don't change the problem. So this is called permutation symmetry, where the symmetry group is the symmetric group on n symbols. And now you have these two symmetries, and now representation theory actually tells you what the optimal measurement is. In the sense, like it lets you guess the optimal measurement, and then you just need to prove that this is in fact the optimal measurement. And this was done by two very important papers by Leditzky et al. In the 80s, and then Kyle and Werner in some 10 years later. And so this is a very nice example where using the symmetries that you have in the problem let you find out kind of like an optimal way to solve this problem, information theoretically speaking. The reason why this works so well is because these two symmetries, the unitary symmetry and the permutation symmetry, play nice with each other in terms of the representation theory involving the two groups. And there's a thing called Schur-Weyl duality, which imposes a nice structure on the problem that you can exploit in the mathematical explanation. And I will tell you later how that actually works. And in this paper and in this talk, our goal is to find and exploit these symmetries in quantum teleportation protocols. So quantum teleportation is arguably one of the most important quantum information processing tasks. It was devised by Charlie Bennett and these 5 other people in the 90s. And it really, in some way, it really kickstarted quantum information theory, at least in my opinion. And the idea of quantum teleportation is that you combine two resources, shared entanglement between two parties that are spatially separated, and classical communication in order to implement a quantum channel between these two parties. So using these two resources, they can send each other quantum information. I will explain in more detail how this actually works. And the goal in this talk is to discuss a variant of teleportation called port-based teleportation, where we have these permutation unitary symmetries built into the problem, and we can exploit them to analyze it. Okay, so this is the outline of my talk. I first have to get some preliminaries out of the way, mainly just in order to make sure that we talk about the same thing. I will then talk about teleportation protocols, first the standard protocol, and then I will define port-based teleportation as a variant of the standard protocol and describe its most important properties. And then there are two main protocols that we usually talk about. One is called the standard protocol, and the other one is the fully optimal protocol. And I'll start with the standard protocol and explain in detail the kind of symmetries that the problem has and how we can use them, which will allow us to kind of analyze the protocol and find the optimal performance of these protocols. I will then show, not really prove, but show how to generalize this to the fully optimal protocol. And then I will conclude with some remarks. Okay, so just as some preliminaries, what's going to be very important for us is a maximally entangled state between two separate parties. If you have two qubits, then this is the famous EPR state, where you have two, say, spin systems, spin 1/2 particles, and the maximally entangled state between those will be an equal superposition between both systems in the up state and both systems in the down state. We want to talk about qubits, so quantum systems with local dimension d, which can be greater than 2. And in this case, we again have a maximally entangled state, which is kind of defined analogously. So we take some basis for the A system, and we assume the B system is identical, so you have the same basis in the B system. And then the maximally entangled state will just be an equal superposition of the tensor products of these basis states. And you normalize. So this state will play an important role in our discussion. The other thing that will play a very important role is kind of like the basics of representation theory. So what is a representation of a finite group? We have some vector space V, and a representation of a group G on this vector space is a map that maps each group element into a linear map acting on this vector space, such that the group multiplication is preserved. So in technical terms, this is a group homomorphism from the group into the endomorphism group, or general linear group on this vector space. And a very important concept in representation theory is the so-called irreducible representations, or irreps, as people call them to save some time. So when you have a representation space and you let the group act on it, then sometimes there are some invariant subspaces. And an irreducible representation, or irrep, is a representation space that has no G-invariant subspaces other than the trivial ones, because the zero space and the full space are always subspaces of a vector space. But if there are no other G-invariant subspaces, then we call this representation irreducible. And the reason why this is such an important tool in representation theory is Maschke's theorem, which tells you that these irreps act as the building blocks in representation theory, in the sense that whenever you have some representation B of a group, you can always decompose this into irreducible representations. So in choosing some basis, when you have matrices describing these linear maps, then you will have this block form where these boxes here correspond to the irreducible representations. And then we'll talk about how these look for the two groups that we usually deal with. Okay, so these are just preliminaries. I hope everything is clear. Everyone's on the same page about this. If there are no questions, I'll continue with talking about teleportation, which is the main object of this talk. So as I said in the introduction, the idea of teleportation is to combine two resources to get a third one. And so we assume that we have two parties, Alice and Bob, who are in separate labs, but they share an entangled state. So they have some correlation between their two labs. Let's assume for simplicity that this shared entangled state is just a maximally entangled state on qubits. So A1 and B1 here are qubits. A1 is with Alice, B1 is with Bob, and the two are maximally entangled. And the other resource that Alice and Bob have is a classical channel from Alice to Bob. So Alice can just call Bob up and tell him some information, and then Bob can do something based on that classic information. And now the goal in teleportation is to use those two resources, the entanglement and the classical channel, to teleport a qubit from Alice to Bob. So Alice has a third qubit C in her possession. She doesn't know the state of this qubit. And she wants to teleport that qubit to Bob using the entanglement and the classical communication channel. And the way the standard protocol works is in 3 steps. So first, Alice does a measurement on the 2 qubits in her possession. This is the A1 qubit, which is 1/2 of the entangled state, and the C qubit, that's the one to be teleported. And in the original formulation, Alice will perform a Bell measurement on these 2 qubits. So you can describe the Hilbert space describing 2 qubits with the Bell basis, which are 4 orthogonal maximally entangled states, which form a basis for this 4-dimensional space. Alice performs just a projective measurement with respect to this basis. And there are 4 measurement operators, so she will get 1 out of 4 outcomes from this measurement. And she just tells Bob that outcome of the measurement. And then based on this measurement outcome, Bob applies a correction operation to his share of the entangled state. In the standard protocol, this will now be one of the 4 Pauli operators, identity X, Y, or Z, which he can apply to his share of the entangled state. And then the result of this is that the qubit in C will kind of like vanish from Alice in a certain sense and be teleported into Bob. And this standard teleportation protocol is actually very nice. It's beautifully simple. It's a nice exercise for an undergrad course to kind of like work out that this always works. And the key point is that it always works. So like the teleported state is always teleported exactly, and there's no probability of failure of the protocol. But there's one big disadvantage which prevents teleportation from being applied in certain situations. And that is that Bob has to apply this correction operation to his part of the entangled state. And we say that it's a non-trivial correction operation because based on the measurement outcome, he has to apply one of the 4 Pauli matrices to his state. And the problem with this is that in certain applications, what you want Bob to be able to do is to kind of process the teleported state further without Alice having to tell him this measurement outcome. Okay, so in certain applications, which unfortunately I won't be able to go into detail, but in some applications, you don't want Bob to apply this correction operation before doing something further with that state. And one big application of this is so-called instantaneous non-local quantum computation, where one task that you try to achieve there is, for example, to implement a joint unitary on 2 separated systems A and B. And the idea is that the 2 parties A and B use teleportation to kind of implement this unitary. But if you look at this paper by Bege and Koenig, where they introduced this, you will see that in these protocols, you actually need Bob to be able to do something with the teleported state without Alice actually telling him what outcome she got in the measurement. Okay. And so This is the starting point for port-based teleportation, because port-based teleportation exactly tries to address this shortcoming of standard teleportation. So it is a teleportation protocol where the correction operation is as simple as possible. I will say in a minute what this means. But unfortunately, it comes with some caveats. So there are some disadvantages. You lose the exact nature of the protocol. So instead of an exact teleportation protocol, you now have only an approximate protocol. And the discussion is a little bit more involved than the standard teleportation protocol. But we will see that using asymmetries, this can actually be alleviated in a nice way. Okay, so what is port-based teleportation? We again have a similar situation as before. We have two separated parties, Alice and Bob, and the task is again to teleport an unknown qubit or qubit that Alice has in the C qubit here to Bob using entanglement and a classical communication channel. And this variant of teleportation, which was devised by Shizaka and Hiroshima in the late 2000s, starts now not with one maximally entangled state, but let's say with n maximally entangled states. So each party has n systems, A1 through AN for Alice and B1 through Bn for Bob. And these are called ports, where the name port-based comes from. And let's assume for simplicity that all of like the AI and BI state system are in a maximally entangled state. So whenever I write in diagrams this wiggly line here, I mean a maximally entangled state between the two qubits. And the protocol works in a very analogous way to standard teleportation. So the first step is for Alice to perform a measurement on her systems. Only this time, this is n+1 systems. So the one qubit she wants to teleport and the n qubits or qubits that she shares with Bob. So she applies a joint measurement on these n+1 systems here in this box. She gets some outcome from that measurement. She again tells Bob that measurement outcome. And in port-based teleportation, this outcome is just one of the numbers 1 through n. So it kind of, you can think of it as a labeling one of these ports. And once Bob receives the label that Alice got in her measurement, Bob simply discards all but the ith port if he got the label I. Okay, so here it's the label I is equal to 2. So let's say Alice does this measurement. She gets the outcome 2, tells this to Bob. And Bob now knows, okay, the teleported state or an approximate copy of the teleported state will be in my second qubit B2. So I forget all the other ones, and then I hold, in theory, I hold a copy of the teleported state. Okay. And you can now hopefully already see that this correction operation is now, in a sense, as simple as possible, because Bob doesn't need to further process his qubit that holds the teleported state. Okay, all the Bob has to do is kind of forget all the other ones. Mathematically, this just corresponds to tracing out the other qubits. And we can capture this kind of idea that you don't have to process it further by saying that the resulting protocol is unitarily covariant, which means that this correction operation, the partial trace over all but one port, commutes with an arbitrary unitary that Bob can apply to each of his ports. Okay, so this is the unitary U here that he can apply to each of his ports. And he can do this before the protocol. And then when they run through the normal protocol, what they will actually teleport is not the state psi of the qubit C, but it's the processed state psi, and it's processed by this unitary U. And in the literature, this has been called a universal programmable quantum processor, because it allows you to kind of implement an arbitrary unitary on your teleported state. But that's actually where the problem lies, because it was proved by Nielsen and Chuang in the late 90s that protocols that implement such a universal programmable quantum processor cannot be perfect with finite resources, because it basically violates quantum mechanics if you do that. Okay, so if you take finite resources, which in our case would mean that the local dimension of these systems is finite and that we have a finite number of ports, so the D and the N will be finite, then this no-go result by Nielsen and Chuang tells us that this protocol, whatever it does, cannot be perfect. And now the goal is somehow to make sure that we get a way to better and better approximate our target state. So we lose something by making the protocol unitarily covariant, but we win something by having this unitary covariance property. Okay, and this enables some applications of porpoise teleportation, which are not possible with the standard teleportation protocol. So the one that I've mentioned is this instantaneous non-local quantum computation, where the task is, for example, to implement a joint unitary on two separate systems. And this has been used as an attack on something called position-based cryptography, where you have like you verify your position against adversaries. And it also has some other applications in, for example, quantum channel discrimination or in quantum communication complexity. And these are all applications where the standard protocol with this correction operation that Bob has to do kind of prevents you from using it. But this porpoise teleportation with this kind of like simple correction enables these applications. Okay. So we now know that porpoise teleportation, because of this no-go theorem, cannot be perfect. So in a sense, you know, you can see teleportation. The goal of teleportation is that you implement some kind of qubit channel. And ideally, this would be a perfect channel, an identity channel that just maps the state unharmed or undisturbed from Alice to Bob. With porpoise teleportation, because of this no-go theorem, we know that this is not the case. So we know that this teleportation channel that we get from the protocol will only approximate the identity channel. And now a natural question to kind of gauge the performance of the teleportation protocol is to ask, how close is my channel to the identity channel? Like how much noise do I have when I do this teleportation? How much do I disturb the teleported state? And a good way to measure a distance between quantum channels is the so-called entanglement fidelity. To define this, what do we do? We assume that Alice actually has two systems in addition to her ports. So like a qubit C that she wants to teleport and a qubit C double prime that she wants to keep. And we assume that they are in a maximally entangled state. And then you teleport one half of this maximally entangled state to Bob. And then you ask, how close is my resulting state to the initial maximally entangled state? So the entanglement fidelity is exactly measuring that. It's measuring the overlap of the initial, of the initial entangled state that you start with this noisy version of the maximum entangled state that you get when you use the teleportation protocol to teleport one part of this. Okay, and so this is a fidelity quantity. So it's 1 if and only if the channel is perfect, and it's 0 if the channel is completely useless in a way. And our goal is when we now want to find protocols, our goal is to find channels such that this entanglement fidelity is as close to 1 as possible. Okay, and in order to do this analysis and kind of like determine the entanglement fidelity of porpoise teleportation protocols, Ishizaka and Hiroshima, when they devised this protocol, they had a very fundamental insight into this problem. Namely, they realized that teleporting half of a maximally entangled state from Alice to Bob through these ports is actually equivalent to a certain state discrimination problem. And in more detail, it's equivalent to distinguishing these states, eta, I. I've tried to kind of schematically depict them here on the left. So what you do is you trace out all but one system on Bob's side, and then you consider the joint state of all of Alice's ports and this one system that Bob has. If this is the first system, then this is the state eta 1. If it's the third system on Bob's side, it's the state eta 3, and so on and so forth. Okay, so you have n states, and they have some overlap on the A system. So this is, this is a non-trivial state discrimination problem because they are not orthogonal. And then we furthermore assume, like in a state discrimination problem, you always have a prior on your states. So you kind of like imagine that you draw the states with a certain probability, and then you try to detect the state. Here we assume that we actually have a uniform prior. So we have n states, so the uniform prior will be 1 over n for each state. And then Ishizaka and Hiroshima realized that the success probability in the state discrimination problem is proportional to the entanglement fidelity of the teleportation channel, lambda. Okay, and the proportionality factor is this n over d squared, where, as a reminder, the d is the local dimension of all of these systems, and the n is the number of ports that we have in the game. And in fact, this equivalence doesn't only hold for maximally entangled states between Alice and Bob, but for arbitrary port states. So this is like a nice exercise to do this. And this correspondence between port-based teleportation and state discrimination is very useful because state discrimination is a very nice problem, mathematically speaking. So when you have a generic state discrimination problem where you have some states A to I, which can now be arbitrary, with certain prior probabilities Pi, then your goal is to maximize the so-called success probability, which is given by this functional here. So you just you have some measurement EI, which is in the most general setting POVM, a positive operator valued measure. So you have some, for each state you have a measurement operator EI. They all need to be positive semi-definite, and they need to sum up to the identity on the space, which is kind of like the conservation of probability. So you need to get one of the outcomes. And then you weigh these probabilities by the prior probability Pi of drawing that state, and then you sum over all of these, which gives you the success probability. And this optimization problem, optimizing over all measurements such that you maximize the success probability, is actually a very nice optimization problem. It's a so-called semi-definite program, which means that you have basically the semi-definite refers to the fact that here in the constraints you have semi-definite constraints. So these EIs are matrices and they need to be positive semi-definite. So this is a bit strictly more general than linear constraints, for example. And the nice thing about semi-definite programming is that to a primal problem P, primal always means that you maximize something. There's a dual problem D that you can formulate. There's a way to do this. I won't go into detail of how to do this, but the state discrimination problem has this dual problem where you minimize the trace of a certain operator K that needs to satisfy this relation. So this is the positive semi-definite Löwner ordinal matrices. So this just means that K minus this operator is a positive semi-definite operator, and this needs to be satisfied for all I. So for each of the states that you want to distinguish. And the nice thing about this particular semi-definite program is that you have something called strong duality, where the two optimization problems actually give you the same answer. So instead of solving the original maximization problem, you might as well solve the minimization problem, which might be easier in certain ways. We will later use this actually to prove optimality, and I will show you how to do this. Okay. So we have this connection between port-based teleportation and state discrimination. And as a reminder, we're in a situation where the port state consists of n maximally entangled states. So this is this state here. And then in a state discrimination problem, we want to distinguish these states A to I, where each A to I consists of all of the A systems and Bob's ith system. So if you trace out the B systems, then you will get this form here. So this is a state that's maximally entangled between AI and BI and completely mixed on all the other A systems. And we have these uniform probabilities. And so now we, instead of kind of like determining the entanglement fidelity by this correspondence, we can just try to maximize the success probability in this state discrimination problem. So this is this formula here. And I told you that kind of like the variable that we have in this problem is the measurement. Okay, so we want to optimize this quantity over all POVMs or measurements that Alice can implement on her side. And so now a natural question is, what is a good choice for this POVM, for this measurement? And it turns out that there is a choice that is pretty good, and so therefore it's called the pretty good measurement. It's sometimes also called the square root measurement because of the fact that the measurement operators EI are defined in terms of the inverse square root of these average states. So what do you do to get these measurement operators? You take all of your states that you want to distinguish, you add them all up, and you get an average state. And then the measurement operators will be the state you want to detect sandwiched by these eta bar to the -1/2. Okay. It's a little peculiar why this is defined like that, but it makes a little more sense when you then check that this is in fact a POVM, a measurement. So for that, you need to check that these measurement operators are positive semidefinite. This is satisfied. This is an easy exercise. And then when you sum them up, you want the identity. Remember, I told you like a POVM always needs to kind of like conserve probability. Here, there's a technicality. If this eta bar state is not invertible, then this inverse here is only defined on the support. So when you sum them all up, you don't get the identity on the full space. You only get the identity on the support of this eta bar average state. But this is fine because kind of like the support of this eta is all you care about. So what you do is you restrict your Hilbert space so that this support operator here just becomes the full identity again. Okay, so this is just some technicality. And the use of this pretty good measurement is that Barnum and Knill in a paper of 2002 realized that in a generic state discrimination problem, this pretty good measurement always does a pretty good job. So if you have, let's say you have the optimal success probability P opt, then you're guaranteed that the success probability from using this pretty good measurement will never be worse than the square of the optimal success probability. Okay, and if you can make the optimum probability converge to 1, for example, in some limit, then you will also know that the success probability coming from the pretty good measurement will converge to 1. Okay, and this is basically what we're trying to do. So we kind of now want to use this pretty good measurement and show that as you take the limit n to infinity, which means that you add more and more ports, you want that this success probability approaches or kind of like behaves like d squared over n, because then by the correspondence between port precipitation and state discrimination, you will get that the resulting protocol actually is perfect in the limit of infinite number of ports, okay, which is kind of the goal. So in a sense, even though the protocol is not perfect, we know that from this no-go theorem, because with finite resources, it cannot be perfect. So what you do is you make it better and better by adding more and more ports, such that in the limit of an infinite number of ports, you actually get a perfect protocol. The fidelity approaches 1 in the limit. And the main result of this paper that I'm talking about is in fact to prove that the pretty good measurement is not just a pretty good ansatz to achieve this limit, it's actually the optimal measurement. So port precipitation is somehow a task where the pretty good measure is in fact the optimal thing to do. Okay. All right, I think this is a good time to stop and ask if there are some questions.
Felix, yes, there was one question back when you were introducing port-based teleportation. Pywens, I asked, if this protocol requires a classical channel, is it still instantaneous?
It depends on what you mean by instantaneous. So kind of before Bob receives the classic information from Alice, the target state is somehow spread out over all the ports on Bob's side. So before Alice tells Bob the outcome, it's not a useful protocol. This also holds for standard teleportation protocol. So these people sometimes use this to prove that these teleportation protocols actually don't violate causality, because the classic communication is restricted by the speed of light, so that you don't actually have instantaneous. You don't have instantaneous transmission of information, of quantum information. I hope this answers the question somewhat.
Makes sense. I think that was the only question.
Okay, cool. Great. Okay, so we kind of know now, hopefully, what port-based teleportation is, what it's trying to achieve. And we have this useful connection between port-based teleportation and state discrimination. And so now what we want to do is we want to solve the state discrimination problem. And we want to do this using the symmetries that we have in the protocol. And the thing to start with, or kind of like the first insight, is something very well known. Namely, it's a fundamental symmetry that the maximally entangled state has. So you have a maximally entangled state, which is a bipartite state on two isomorphic systems A and B. And then if you act with a unitary U on A and with the complex conjugate unitary on B, then the maximally entangled state will be invariant under that. Okay, this is an easy exercise to prove. And remember that the states that we want to distinguish in our state ensemble are exactly maximally entangled states between one of the A systems and the B system, and completely mixed states on the rest. So here I've again put a schematic depiction of the eta state. This is the eta 1 state. And so we have one maximally entangled state between A1 and B1, and maximally mixed states on all of the other A systems. And so on this maximally entangled state here, I have this U tensor U star symmetry that I get from the maximally entangled state. And obviously a completely mixed state means it's proportional to the identity. And that is always invariant under any unitary, right? Because they just cancel. So that I get unitary invariance also on the other A systems. And if I take those two green things together, what I have in summary or in total is that I have a U tensor N tensor U star symmetry on these eta I states. Okay, so the U tensor N acts on all of the A systems, and the U star acts on the B system. Okay, and so this is just the commutator of these two. So this means that they commute, which is another way to phrase the symmetry. So this is the unitary symmetry. The other thing we're looking for is permutation symmetry. And here it's easy to see that this part of the state, this completely mixed state on all of the A systems, is naturally invariant under any permutations of these n-1 A systems. So I have kind of like a restricted Sn-1 invariance, Sn-1, because obviously if I permute the A3, say, with the A1 system, I will get a different state, right? I will actually get the eta 3 state. So I have this kind of restricted permutation symmetry, meaning that if I have some permutation that acts on all A systems except for the AI system, for the eta I state, this is again a symmetry of the problem. Okay. So this is the symmetries for the eta I state. Let's look at the average state, eta bar, where we sum all of these eta I states up. This is now good because again we have the unitary invariance in the same way as before. Okay, so this is now just kind of like a sum of maximally entangled states between A1 B1 and then A2 B1, A3 B1. You know, like all of these BIs are identical to the same B system. So I've just distinguished them here, but in fact it's just the same system. So I have again this unitary invariance. So I get again a U tensor N on A tensor U star on B symmetry. But now the cool thing is that if I add all of these eta states up, I also now have a full permutation symmetry. Because now if I do a permutation and I do permute this A1 system somewhere else, this will appear later in the sum, right? And so kind of like I just shift these states around, but the sum stays invariant. So now I get a full permutation invariance under the full Sn permutation group, okay? So this is strictly more than before. And I have now these two symmetries, the unitary symmetry and the permutation symmetry. And I mentioned in the introduction that these two symmetries kind of play nice with each other. And so let's go into a little more detail how that works. So our representation space is n tensor copies of a d-dimensional Hilbert space. Okay, so these are the blue balls here. Each one is a d-dimensional Hilbert space. And I have my two symmetry groups, the symmetric group Sn and the unitary group Ud, acting on this representation space. The symmetric group just acts by permuting the tensor factors. Okay, so schematically, you can imagine something like this, where the first system is mapped onto the second system, the third onto the first, and so on. Mathematically, you can define the action on product states, and then you consider the linear extension to the full space. This is the first symmetry. The second symmetry, like the action by the unitary group, is just given by acting with the same unitary on each state, on each tensor factor. Again, you can define this on product states and then extend linearly. And now the crucial thing to realize is that the two actions commute, which I hope is clear from the way I drew this picture. So it doesn't matter whether you first permute the systems and then act with the same unitary in all the systems, or you first act with all the unitaries and then you permute, right? So this is because of the fact that you act with the same unitary on each system, basically, okay? So these two representations commute. And what's more, they don't just commute, but they actually span each other's commutant, which is something I don't want to explain in detail, but just in short, a commutant is the set of all operators that commutes with a certain set. And so this, what I mean by spanning each other's commutant is if I have an operator that commutes with all unitaries that come from the symmetric group action, if I have an operator that commutes with all of those, I know it's going to be in the span of unitaries acting in this way, okay? And the same holds the other way around. If I have something, if I have an operator that commutes with U tensor n for every unitary, I know that it's going to be kind of like in a linear span of these permutation operators that I have here. Okay, so this is just a mathematical statement. For these two particular groups, Sn and Ud, this is called the Schur-Weyl duality because it was kind of found by Schur and Weyl. And the nice thing is now that we can use this duality and this commutant structure to decompose our representation space into the irreps of Sn and Ud in a way that I mentioned in the preliminaries. How do we do that? Just as a reminder, an irrep or an irreducible representation of a representation is a space that doesn't contain any non-trivial invariant subspaces when the group acts on them. So these are kind of like the building blocks. And for the representation theory of the symmetric group and the unitary group is very well known. It's a classical result from representation theory. They're both indexed by partitions mu of an integer n. By partition, I mean kind of like numbers mu1 through mu d that sum up to n. And I also assume that they're actually ordered. So they're non-increasing from mu1 to mu d. And now I will always consider partitions into at most d parts. Okay, so there can be at most d constituents for the integer. And there's a nice way to graphically relate partitions to so-called Young diagrams, for which you just take n boxes and you assemble them such that the length of the ith row is equal to mu I. Okay, so if, for example, I have a partition of the integer 12 into 4 parts, one possible partition is 5, 3, 3, 1, and then I take 12 boxes and I arrange them such that the first row has 5, second and third row have 3, and the last row has 1 box. Okay. And it turns out that these objects, these Young diagrams or these ordered partitions, parameterize the irreps of the symmetric group and the irreps of the unitary group. Okay, so there's a way to construct these irreps, which is to say you can construct these vector spaces. For the symmetric group, these are called Specht modules, and for the unitary group, they are called Weyl modules. Construction will not be important. What's important for us is that these representation spaces have known dimension, and we call the dimension of the irrep for Sn d mu, and the dimension of the irrep for Ud n d mu. Okay, so where in both cases the mu just corresponds to this Young diagram. Okay, and then when you use this knowledge, you can now decompose your representation space, these n tensor factors of CD, of the d-dimensional Hilbert space. You can now decompose that space into the irreps of the two groups. So you have a direct sum, which is kind of like this block structure in the matrix that I showed you before. It runs over all partitions of n into at most d parts that are ordered. And then I have in each kind of sum end, in each block of this matrix, I have a tensor product of the irrep for the unitary group and the irrep for the symmetric group. Okay, so this is what I meant by the two representations play nice with each other. you can kind of like decompose the full space into the irreps for both groups, and then you know that in each component, you know exactly how the two groups act. Like the unitary group will only act on this first factor here and act as the identity here, and the symmetric group will only act on the second factor, and it will act on the identity as the identity on the first factor. Okay, so this is very useful when you want to compute things with it. And the way that we will use this Schur-Weyl decomposition is with an application of Schur's lemma, which is one of the most important but still very easy results in representation theory, which in our situation tells us that if we have a state rho on our representation space that is invariant under both actions, so it's invariant under all permutations, and it's invariant under all unitaries acting in this particular way, then an application of Schur's lemma tells us that actually in each of these summands here, the state has to be proportional to the identity. Okay, so I can decompose, I can find a particular basis, which is called the Schur-Weyl basis, in which rho looks like a block matrix, and there's more structure to it. In each of these blocks, it's proportional to the identity, and the proportionality factor is just an eigenvalue of rho. Okay, so these numbers R mu. Since rho is a density operator and always has non-negative eigenvalues, these R mu's will always be non-negative too. And then we have this normalization condition to ensure that rho is an actual density operator, which means that the trace is equal to 1. Okay, if you take the trace of this thing, then you just get this normalization condition for the R mu's. And so this is now exactly this kind of like imposing structure that I was alluding to in the introduction. Okay, if I have a state, and we identified before that our states in the state discrimination problem have these symmetries, they are invariant under these two group actions, right? And so using this, we can actually now infer that they have a very simple structure, and the number of degrees of freedom in these states is actually very little compared to the full dimension of the space. Okay, so that's the huge gain that we have when we use symmetries. There is a caveat, because if you paid attention, we don't just have the U tensor n symmetry in the Schur-Weyl duality, we also have this U star thing. So remember, we had these states eta I, and on the B system, we had the complex conjugate of the unitary acting. So we have here an additional tensor factor in our representation space, which is not affected by any permutation, because the permutations only ever act on the A systems. But it is affected by the unitary acting as a complex conjugate on it. But luckily, there is a nice way to incorporate that symmetry into the Schur-Weyl decomposition. This is called the Pieri rule. I will not go into detail here. It's just if you consider your representation space as a tensor product of this additional dual representation of U and the decomposition that you already have, then you can kind of like incorporate that into this decomposition, and then you get like a slightly more involved decomposition of your state into like another block structure where you now have two kind of pieces of data. You have a partition of n-1, which corresponds to the fact that you had the symmetry group Sn-1 acting on the states, if you remember. So you take some Young diagram on n-1, and then you take Young diagrams that you obtain from adding a single box in a row where you can do that. Remember that these Young diagrams, the length of the rows have to be non-increasing. So if you have two rows with the same length, then you can only add a box in the upper row. So if you allow me to go back quickly, in this Young diagram, I could add a box in the first row. I could add a box in the second row. I cannot add a box in the third row, because then the third row would have 4 boxes and the second one 3, and we don't allow that. Okay, the lengths have to be non-increasing. Okay, but if you sum over all the Young diagrams you get where you can add this box, you get another Young diagram mu, which is now on n boxes instead of n-1. And then again, we have this nice block diagonal form where we have these eigenvalues S mu alpha, and the rest is just an identity. Okay, so we can again use this nice structure. It's a little more complicated because of this dual representation, but we can still use the information we get from the Schur-Weyl duality. That's kind of the takeaway here. Don't worry about the details. Okay, and so now we want to use these insights. We want to use these this nice structure that we have to actually solve the state discrimination problem. So remember, we have the n states a to I, which are just a maximally entangled state between ai and bi, and a completely mixed state on all the other systems. They come with uniform priors, and we chose this pretty good measurement, which is composed of these states sandwiched by these inverse square of the average states eta bar. And these eta bar states have the nice full permutation symmetry. And so now we want to compute this success probability functional. So we want to compute this expression here. The PIs for us are just 1 over n, so we can pull this out. And for EI, we can insert this form for the pretty good measurement. And so now this already looks like a little nicer than before. And now remember that we have these like nice decompositions of our operators. The eta bar can be decomposed using this Pieri rule applied to the Schur-Weyl duality. And the eta I bar, the eta I state is even simpler because it's just plain Schur-Weyl duality combined with the maximally entangled state. And I will not go through the details of how to do this, but then you can actually plug these expressions into this trace and then do a careful manipulation. And then you end up with a formula, which is very nice, and it was actually first proved in a series of very nice papers by Michael Studziński et al., where you now get an expression for the success probability in terms of these dimensions of the irreps of the two groups. So kind of we use representation theory to really get a closed formula for the success probability of the state discrimination problem. And then via this correspondence, we now also get an explicit formula for the entanglement fidelity of corpus interpretation. Okay, and the way this works is like it's kind of derived from this adding a box procedure that I explained before, where you sum over all Young diagrams or partitions on n-1, and then you consider another sum over all the diagrams you get from adding one box in a place where it is allowed. Okay, and then you evaluate this product of the two dimensions. Okay, so this is a kind of like representation theory allowed us to actually get a nice explicit expression for the success probability. What we haven't argued yet is that this is actually the optimal one. So what we did is, remember, we had the state discrimination problem where you have the freedom of choosing a measurement. We chose a particular one, the pretty good measurement, and we were able to actually compute things. But now we also want to ask, is this actually optimal? And the answer is yes, luckily, it is optimal. And we can use this semi-definite programming duality that I showed you before to do this. So remember, instead of computing the maximal success probability using these measurements, I can go through the SDP duality to rephrase this as a minimization problem. And the minimization problem in our case was that we need to find an operator K that satisfies this constraint for all of the states. So the PI again is 1 over n for us. And then the value of the optimization problem will be given by the trace of this K. And the idea is now to make a judicious choice for this operator K, such that the trace of it is exactly the expression that we get. And then we're done once we show that it's feasible, which means that it satisfies all of these constraints. And since it's a dual program, you usually call these things dual feasible when they're feasible in a dual program. And so this operator K, it looks a little weird, but it's actually just literally taking the success probability from before and forgetting the trace, because we do take the trace afterwards. So we are kind of guaranteed that by construction, this will have the same trace. And all that is left to show is now to prove that this is actually greater in the positive semidefinite order than the states that I want to distinguish. Okay, so which reduces to this relation here. And you can again use this, show this using the nice structure you have for the eta states. So you can again use this block structure you get from representation theory to make sure that this relation is actually satisfied for each I. Okay, and again, I will not go through the details. You can find those in the paper. But so this is a very nice kind of like interplay of representation theory and semi-definite programming, where first you use representation theory to kind of make a guess for the optimal measurement. You compute something, you get an answer, and then using the duality theory of semi-definite programming, you can actually make sure that it's the optimal solution to the problem, which is very nice. Because usually it's very hard to do this, and porpoise teleportation is one problem where this is very you can do that and you get a very nice answer. Okay, any questions on this part?
Yes, there was one question by Marius Junge. Marius was wondering if you want to say something about the success probability for mid-sized dimension. Like, can you do it with a real computer? And I guess how many qubits?
Sorry, repeat it once more. The success probability for infinite dimensions?
Mid-sized dimension. So I guess kind of what happens in practice is the way I understand Marius.
Oh, yeah, very good answer. So this is not part of this talk, but in the prequel to the paper that I'm talking about, what we did is we actually looked at the asymptotics of these protocols. So where you get a bound on these fidelities as a function of the n, as a function of the number of ports, which you can then use to gauge the performance in real world applications if you actually want to implement this. And obviously also, I mean, for you know, for kind of like small d and n, you can just numerically compute this, which will give you an answer. It's just, it's a little more challenging to determine the limit of these things, and this is what we did in the other paper. I'm happy to kind of like give the reference for this later. But for kind of like small instances, you can just compute the sum, and then you will get the performance of a pretty good measurement. Yeah.
Makes sense.
Okay. Any other questions?
I think this was it.
Okay, great. Okay, so I'll come to the last part of my talk, which is to kind of generalize this. So far we've talked about porpoise teleportation, where the entangled state that the Alice and Bob share in the beginning just consists of kind of copies of maximally entangled states. And then we detected the symmetries in this port state, and that allowed us to compute the entanglement fidelity, or the success probability in the state discrimination problem. So in theory, one might think that you could achieve an even better fidelity if you try to optimize over the port state instead of fixing it to be a specific thing. So this is actually, okay, so here, very good. Here, this is the paper that I was talking about before, this archive reference here. So what we did in this paper is we kind of looked at the behavior of these teleportation protocols in the asymptotic limit and tried to see what is the behavior with n of this entanglement fidelity. And you will find that for the standard protocol, where you have n maximally entangled states with a pretty good measurement, which we know is optimal, you get an asymptotic behavior of the entanglement fidelity of 1 minus something that decays like 1 over n. And the proportionality is just a function of the d. It's d squared minus 1 over 4, actually. And now you can ask, do I get a better asymptotic behavior if I try to optimize the port state? And the answer is yes, because you can actually improve this this kind of like first order correction to the fidelity to 1 over n squared, which means that it will converge faster to 1, right? If you take the n large. And so you do want to now analyze these more general protocols as well. And one thing that greatly helps here is the realization that first Christian Mayens, one of my co-authors of this paper, had in his PhD thesis, and we kind of like spelled it out more in this paper. It's the realization that if you have an arbitrary port state, and I've kind of like tried to pictorially, you know, this is just like something arbitrary, yeah, like kind of like a Haar random state or whatever. So the realization is that you can always symmetrize the port state so that you enforce the symmetries that we had in the first part of the talk. Okay, So your goal is you symmetrize the port state so that you again have the permutation symmetries on the A systems and on the B systems, and you have the unitary symmetry with an arbitrary unitary acting on each system. Okay, and you can prove that if you take an arbitrary port teleportation protocol and you symmetrize, the entanglement fidelity will not go down. It will stay the same or even go up. Okay. And in more detail, what you get when you do the symmetrization is that you can turn this entangled resource state into you can actually always assume that it's pure. That's kind of like a related result here. And then furthermore, enforcing these symmetries, you can assume that it's a symmetric purification of a Werner state. Okay, Werner states are just states that have the U tensor n symmetry. And so explicitly, what you can assume is that your port state rho A and B n is just some pure state where you again take n maximally entangled states, and now you have this kind of O operator which acts on it. And this operator again has the symmetries that you want. So it has a U tensor n symmetry, and it has this permutation symmetry. So this O operator is in a way a symmetric Werner state, if you will. Okay. And we can again use these two symmetries together with Schur-Weyl duality and Schur's lemma to infer that this operator has a very nice structure again. It again has this block structure, where in each block it's proportional to the identity, and the proportionality constant will be some constant C mu that will show up later. And then you can again ask, okay, what is the optimal measurement here? And the result, which turns out to be very nice, is it's again a pretty good measurement. It's just not the one you think it is, because I have a different port state now, right? Because I have these OAN operators acting on my maximally entangled states. But it turns out that the optimal measurement is just forgetting this O thing here and just taking the very same pretty good measurement that we used before. Okay, so it's again the pretty good measurement that tries to distinguish these states eta I, where eta I is again just the maximally entangled state between AI, BI, and the completely mixed state on the rest of the A system. So you kind of like drop the O operator, even though it's there in the success probability, but somehow for the measurement you don't need this, and the pretty good measurement with respect to these states will again be optimal in the state discrimination problem. Yeah, so this is just in formulas what I just said. So the pretty good measurement is again the same one as before. It doesn't feature these O operators, but then you go through kind of like the same steps as I showed before. You again compute the success probability, and then the answer is very similar to before. You have the same kind of sum, only now you have these C mu constants appearing that parameterize this O operator. And you obviously want to take the best one because the symmetry kind of leaves these C mu parameters free, so you can choose them. So you want to maximize them. You want to choose the best ones in order to maximize the fidelity. And so the entanglement fidelity will be proportional to this functional. But it's again like an answer in terms of representation theory. You have again these dimensions of the irreps appearing and these C mu constants, which are the eigenvalues of the Werner state. Okay, and that was it. So to conclude, we looked at port-based teleportation. This is an approximate teleportation scheme, but it has a very nice property called unitary covariance that enables interesting applications. And we can use this unitary covariance and the permutation symmetry to characterize the performance of these port-based teleportation protocols using representation theory. And we use semi-definite programming techniques to show like optimality of certain measurements in these protocols. And then two very natural questions. One, because that's what experimentalists usually ask when they see the pretty good measurement, they're usually like a little, okay, this involves all the qubits. This is very hard to do. Do you have something that's easier for us to do? So a very nice question is, can we somehow approximate or replace the pretty good measurement with something that is feasible in a sense that it only affects like a certain fixed number of qubits, for example? Or you could do something adaptive maybe. The other question is a little more general. This unitary symmetry and the permutation symmetry, they're ubiquitous in quantum information theory. They've been known to feature in spectrum estimation and quantum state tomography. So the hope is that these tools, especially kind of like using this Pieri rule to have these like more refined symmetries and semidefinite programming, the hope would be that we can use these tools also to analyze the behavior or the performance of other quantum information theoretic tasks with similar symmetries. And with that, I'd like to conclude. Thanks.
Thanks, Felix, for a very interesting talk.
Sorry for being a little over the time.
Yeah, we're a little over time, so I think a number of people have already had to leave. I see there is one question already by Marius. Yeah, if others also want to kind of just say your question out loud, I can allow you to talk. Just kind of let me know over chat. But Marius asks, this appears closely related to Definetti type theorems. Do you have any comment on that?
The symmetries are definitely very related to Definetti type arguments. For teleportation protocols, I would say you're not really interested in approximating states with separable states, which is kind of like one application of Definetti theorems. Yeah, I don't know if that answers the question or addresses the question. But certainly, like, the techniques are very overlapping. So kind of like, I didn't show the calculation, but in actually calculating the trace of these operators that have the block structure, you use techniques that you also use to prove Definetti theorems. So there's definitely a mathematical connection. I don't know if there's an information theoretic connection per se.
Marius says good enough. Okay. Any other questions from the audience?
I'm happy to answer questions by email if people have a more detailed question.
Thanks. I guess I had a quick question. So I wasn't sure if I caught the fidelity result correctly. So if we increase kind of the number of copies of so number of AIs by one, we get 2 more digits of accuracy in terms of fidelity. Is that the right way to interpret what happened there with the n to the -2 dependence on fidelity, or is n something different? Okay.
No, the n is the number of ports. One thing to note here is that in this, so these are results in the other paper, which is here, which is together with some co-authors. One thing to say is that for the standard case where we have this 1/n dependence, we actually know the exact coefficient here. Whereas for the fully optimal case, we only know the n dependence. So we don't have a closed expression for the d dependence of the constant in front of here.
I see.
So you have to be a little careful with kind of like you add 1 port, you get like an accuracy of, so and so. Here, this is a little more involved.
Yeah, asymptotically, I guess. Yeah.
But asymptotically, it's a 1/n squared dependence. So like once you have access to a large number of ports, it's going to be better for you to use the fully optimal protocol.
Makes sense. Okay. Yeah. Awesome. Let's see. Is there any other questions? I guess that's everything. Thanks again, Felix, for a great talk. And
yeah, thanks for having me. Looking forward to being there in person in January.
Right. Look forward to meeting you in person, hopefully.
Yeah, sounds good. Cool. Bye.
Rest of your day, everybody. Bye-bye.